Now we're going to look at methods of heating hot water. The key objectives for this part of the session are for you guys to be able to state which heat sources might use fossil fuels and which might use renewable methods. Also identify what do we mean by fossil fuels, things like natural gas, coal, diesel, etc., kerosene. Identify immersion stats and also describe its two key functions. It will do two things as well. One will be obviously control the temperature, and the other one we're going to find out as we go through. And also I want you guys to explain how we should insulate pipework in heated and unheated areas of the property. It will differ. The amount of insulation you need will differ. Whether actually insulation at all will differ. Okay. So heat sources. There's various methods of heating hot water. Most of the methods actually use fossil fuels, and almost all boilers that we're likely to come across in London are going to run on natural gas, which is a fossil fuel. Some might run on kerosene, also known as oil boilers, and very occasionally you might come across sort of back boilers, solid fuel boilers that might be sort of heated by coal, which is also a fossil fuel. All of these are fossil fuels. Coal is obviously a solid fuel. It's very rarely used, but you may come across it in some very old houses or in some rural areas. You can see an example here of a coal back boiler there. So you've got the fire there with a heat exchanger at the back of the fire, which water would sort of flow through and get heated up. You are more likely to come across biomass boilers. Again, these are used more in rural areas than in urban areas. But yeah, biomass boilers actually run on wood chip, and because wood is a renewable resource, they're actually considered sort of quite environmentally friendly, low carbon technology biomass boilers. They burn, let's say, wood. So some of the renewable methods, as well as a biomass boiler, it's also worth being aware of heat pumps and solar thermal systems. We can use both of these for heating up the hot water, but neither of them generate a lot of heat. The solar thermal system actually can generate a surprising amount of heat on a good day, but it's not consistent. It's not consistent in providing sort of a lot of hot water. So both of these will need an extra heat source to top up the heat. Kind of like we talked about when we looked at the cylinders. Sometimes you have cylinders with 2 or more coils, and solar thermal, and also if you had a cylinder connected to a heat pump as well, both of these would need another heat source, potentially another coil. You could use also an immersion heater to top the heat up in those cylinders. Okay. But we'll chat quickly through about solar thermal. Solar thermal panels, they absorb heat from the sun and transfer it into the hot water cylinder. They'd always go into the sort of lower coil out of the two, if it's got 2 coils connected. Can actually give a good amount of heat depending on the weather, but often it won't generate enough heat to heat the whole cylinder up past that pasteurization temperature of 60 degrees C. So it will require another heat source, an auxiliary heat source, to be added. Okay. Worth mentioning at this point, there are solar thermal panels which absorb heat from the sun, and there's also solar photovoltaic panels. They're not one and the same thing. Solar photovoltaic panels generate electricity using like photons, light, and the solar thermal, it just absorbs heat and sort of transfers it into the water system. Briefly going to look at heat pumps. There's 3 main types of heat pumps: ground source heat pumps, air source heat pumps, and water source heat pumps. Each of these just refer to the source where the heat pump absorbs its energy from, essentially. But they all work the same way inside. They all have an evaporator, and a condenser, essentially. So just for example, a ground source heat pump would have lots of pipes running through the ground. Sometimes they'll be dug into channels, and sometimes it will be bored in a borehole straight down. And these would flow through the ground. They would contain salty water brine, which flows through the ground and comes back and then flows over a heat exchanger. And inside the heat exchanger, there will be a refrigerant gas, a gas that actually it evaporates at quite low temperatures, you know. So this, even if you have kind of quite low temperature water flowing over the heat exchanger, it's still causing this refrigerant gas to evaporate as it absorbs the energy from the water. And then that sort of essentially low temperature heat gets transferred through a compressor, gets compressed, and it sort of releases kind of a small amount of high temperature heat. So you take quite a lot of low temperature heat, put it through a compressor, it squeezes the heat out of it essentially, and yeah, and you get some a small amount of high temperature heat. And that's, as that cycle continues and continues, then you can actually get a decent bit of heat, even on a cold day, even on a days where it's sort of snowy outside. You can actually still absorb some heat, and on average, for each kilowatt of electrical energy that goes into this system to work the pump, to work the compressor, you get roughly 3 kilowatts of heat back, because all of that extra energy is being absorbed from the source, be it the ground or the air, or potentially in some cases water. Yeah. Water delivered from heat pumps rarely reach 60 degrees. I mean, that would be an extremely good day if it was up towards 60 degrees. So therefore, like I've said, if you did connect it to a cylinder, it would need another heat source, for example, an immersion heater, or potentially even a gas boiler to sort of bump that heat up, essentially. And you can see in this picture here of how it works. These would be our sort of pipes, which would be full of brine. They would go in through the earth. This is a ground source system. Essentially, it's taking heat from the ground, which would then sort of flow over the heat exchanger, and yeah, and then that heat would be taken out by the refrigerant gas. It's, let's say, it has got quite a low temperature that it releases, which makes it good for underfloor heating. Not so good for traditional radiators. You'd need to oversize traditional radiators because you wouldn't have as much heat going into them, so they can't then transfer as much of that heat to the room. Ground and air source heat pumps are the two most commonly installed. You can see an air source picture up in the top right here. The air would sort of flow over that, and it would absorb the heat energy from the air, and then turn that into a small amount of higher temperature heat. Okay. Electricity. So electricity is another method of heating hot water. Occasionally you can get electric boilers. You don't come across them all that often, but you do often come across immersion heaters, and we've talked a lot about immersion heaters already in this section. Okay. Worth noting, if a system is heated exclusively by immersion heaters, it's going to be cheaper to install, and it's going to take up less space because there's no requirement for a boiler. Immersion heaters, well, what is it? It's an electric element. It's this part here is the actual element, and then inside this sheath you will find this thing here, which can actually be withdrawn, and that's a thermostat. That's the thermostat. The thermostat's replaceable, which is quite handy because this is the part that's most likely to go wrong. And if it is faulty, if it does become faulty, then it's quick and easy to change it because it's sitting there in a sort of metal sheath. And important to note, all thermostats in immersion heaters must have a control stat and also a high limit stat. The high limit stat's there to essentially make sure that the water doesn't boil in the cylinder. It's worth noting, okay, always make sure if you do install or replace an immersion heater or even an immersion heater thermostat, make sure that you consider your own safety. You carry out safe isolation procedure and carry out all the correct procedures to make sure it's safe. Check the overall installation as well. Check the quality of the wiring to it, and if it needs replaced, replace the wiring as well. Okay, and yeah, just essentially make sure that you're safe as you carry out the job, and also your customers are going to remain safe after the job's been completed. So if you want to fit or remove an immersion heater, you'd normally use an immersion spanner. There's lots of different types here. You can see them on the picture on the right there. They can be quite tricky to remove. This is just not going to likely come up with a test, but it's worth maybe noting that sometimes if you give it a wee heat up with a blowtorch, it can kind of make it a little bit easier to remove. Might loosen up some of the old paste or whatever if it's all been stuck in with paste. Yeah, temperature and Limescale. Well, as we know, we set the cylinder start 1/3 of the way up from the bottom of the cylinder, set between 60 to 65. Okay, if it's hotter than 65, it'll reduce the energy efficiency of the system because, as you can see in this lovely picture on the left, that temporary hard water will cause limescale to occur. Limescale will build up on the coil, and then when water flows through through the coil, it needs to heat up the limescale before it can heat up the water, which obviously is going to reduce the efficiency of the system. There's two types of hard water. One's known as permanently hard water and one's known as temporary hard water. Temporary hard water is the one that causes the real issues with the limescale. It contains calcium carbonate. We can actually reverse the issues of limescale if we fitted a water conditioner, or what most people would call a water softener. Quickly look at energy efficiency and insulation now. We've talked about this a few times already in this unit. You know, it is essential to insulate hot water pipework wherever possible, really. But as we've already said, maximum distance that should run uninsulated according to Part L is 12 metres for 15 and 22 mil pipe. Though, I mean, ideally we should insulate all of our pipework, you know, on the hot water side and on the primary side as well. It does also say in the Building Services Compliance Guide we have to insulate all of the pipework going into and out of the cylinder for at least 1 metre, and we also need to make sure the cylinder itself is insulated. We do also need to take extra care if these pipework runs through an unheated area of the house, for example an attic, an unheated garage, under suspended floor. All of these places are going to be very, very cold, and you're not only risking the hot water losing its heat, you're also risking it freezing as well, you know, in these places particularly. So you want to use kind of thicker, more efficient insulation for these in these areas. Okay. And now it's time for your task.